Yeah. So, hello, ladies and gentlemen. It's a great pleasure to be here. My name is Boris Larin. I'm a malware analyst in Kaspersky Lab. We are analyzing different kinds of exploits and vulnerabilities and working on how to protect against them. Um, I'm an author of malware reverse engineering course for universities and a regular writer on ActionScript3. We have prepared this presentation together with my colleague Andy Ivanov, but unfortunately he has some business in Moscow and was not able to be here. So today's talk is about Adobe Flash exploits and how to analyze them. As you probably know, Adobe Flash is infamous to do big amount of security vulnerabilities found exploited in the world. And in 2015, after the leak of zero-day exploit found in the hacking Steam data breach, security community raised the question whether it might be a time to kill Flash. And last year, Adobe finally announced that the end of the life for Adobe Flash will be the end of 2020. Even if Adobe Flash is announced to be end of the life by the end of 2020, we still encounter new samples on a daily basis and expecting for it to continue even after the end of the life date. And during the last 2 years, there have been found 3 security vulnerabilities exploited in the wild. Since the playback of Adobe Flash content is disabled with default in all modern web browsers, criminals adopted new ways to deliver Adobe Flash exploits by embedding them in Microsoft Office documents, where they will be launched without any user notifications. And this is quite popular technique. For example, such known soft security group likes to use it. And recently, this was addressed by Microsoft in security change in Microsoft Office 365. So before we start talking about Adobe Flash exploits, let's remember about basics of Adobe Flash format. So basically, Adobe runs a binary file format known as shortwave flash, and it consists of different tags, some of which can contain bytecode executable by virtual machine. And actually, there are 2 different virtual machines. One is called ActionScript virtual machine, and another one, new one, is ActionScript virtual machine 2. And the code of ActionScript virtual machine 3 also is called as ActionScript3, and is contained in BBC tag. And here you can see the most popular tools to analyze ActionScript3 files. And while these are great tools, each of them has their own pros and cons. ActionScript3 is a great decompiler, my tool of choice, but it's commercial in closed source. GPX decompiler is a great tool, but it's written in Java, so it's rather slow than ActionScript3. And the amazing RBC does. It's a command line ActionScript3 disassembler and assembler, but it's written in quite exotic D language. So what is important to notice here is that these tools, they are not designed to work with exploits. So in the past, the vulnerabilities in Adobe Flash, they targeted not only the interfaces available from the virtual machine, but also the way how Adobe Flash parses their own Flash file format and BBC tag, and also there was vulnerabilities that related to compilation of bytecode. So these are the cases where Adobe Flash incorrectly processes the own structure and the code. And besides that, these Flash files, they could be obfuscated. So there are cases when these tools are unable to process these files, or it's not easy, not convenient to do them. So during our experience with Adobe Flash, we felt that we need another tool that would be simple and stable. It should contain a graphical interface and be easy to work with. Besides that, it should not fail on obfuscated Flash files because it would simply show the assembly instructions. And it also should be easy to just copy instructions to create the RO. And all of this is almost like existing tool for reverse engineering and ROOTCON, but unfortunately, ROOTCON doesn't have support for Flash files. In the past, there were attempts to implement it, but target only outdated ActionScript3. So that's why we decided to implement it. And here you can see our ActionScript3 processor model for ROOTCON. The result of our work is easy to use and quite satisfying. it's already proven itself in the analysis of in the wild flash exploits, and it's very much inspired by Repsodacin. So, on October 10, 2017, we have found a new zero-day used in the target attack by a threat actor known as Black Boris. It was delivered to Microsoft Office document, and it distributed a thin spike commercial malware. We provide information about this vulnerability to Adobe, and they released an advisory and assigned 7 nuggets to this vulnerability. So, when we start analyzing an exploit, it's very important to find out where is the vulnerability. And when we start analyzing this exact exploit, it was not obvious. Here you can see the output of GPX3/gcompiler. So, if you experience it in analysis of exploits, it's obvious where exploitation happens. For example, this function contains code that is a quite common technique for execution of shellcode from the Adobe Flash. And here you can see that there is a check that checks the defined variable is no longer equals to defined value as an effect of triggered vulnerability. So this vulnerability should be triggered somewhere between this value set and where it's checked. And if we will take a look at the compiler output, we will see that there is a very insignificant code that may trigger vulnerability. So where is the vulnerability? And the first hint we get with the help of our ActionScript3 processor model. If we open our Flash file and we will take a look at the functions, we can see that some of these functions contains something what looks like incorrect instructions not recognized by our processor model. So, and take a notice how this information is missing from the output of the compiler. So, before we start talking about vulnerability, let's take a look on how the Adobe Flash processes their own bytecode. Since the source code of ActionScript3 machine is open source as part of the main project, it gives us opportunity to observe it on GitHub. And here you can see that before execution of bytecode, it's verified by Adobe Flash, and we can divide into 3 types by the way Adobe Flash verifies and executes its code. So these types are native methods, just-in-time compiled methods, and integrated methods. So how does Flash distinguish between them? Native methods are defined by the flag and constant value methods. Basically, native methods are treated as built-in functions of Adobe Flash, and they do not have any bytecode. In most of the cases, code will be just-in-time compiled, and one of the cases when code will be always interpreted instead of just-in-time compilation is when this method is a static init, and so basically it's constructor of class, and has a track action block, so basically it's exception handler. So looking back at this function, you can see that this is indeed a static init because it's constructor of class, and it has an exception handler. So this function will always interpret it. Right now, let's take a look at verification. So verification is handled by a verify common function and verify class. It's performed in 2 steps, and it's needed to make sure that execution of all reachable code paths are reachable to be processed. And here it basically calls a verify block function on each reachable basic block. And here you can see the graph of this verify block function. It's a very huge function, and basically it has a very big switch statement that handles pseudo interpretation and verification of each opcode. And if we will take a look at verification of opcode call method, you can see that it always throws a verify failed exception. And what is interesting here is that verify failed function simply throws an exception. It doesn't abort execution of this Flash file. So, and due to the nature of just-in-time compiled code, it's possible to catch this exception from the just-in-time compiled code. And it's very hard to imagine in which scenario legitimate Flash file will need a way to catch their own bytecode verify errors. Looking back to exploit, we can see that this function is called twice. And if we will debug it, we will see that the first time exception is thrown and it's called by exception handler. But during second execution, this exception is not thrown. So this code is executed without verification. So the vulnerability lies in function parse exception handlers. So this function, if method has any exception handlers, this function will create an associated table in the field after all next three checks. And this is what happens when this function is called for this method for the first time. But besides that, it also sets a child from, a child to maximum ranges. And these variables are used to verify our other instructions that may throw an exception. And when this function is called for the same method second time, and it checks the logic of this function is called to check whether if this associated table already exists, then it returns without initializing try from and try to executable ranges. So try from and try to are not set. And when we will come to verify an exception handler, this part of the check will always fail, and it will prevent verification of exception handler. Interesting that this is not the first time, not the first vulnerability related to bypass or verification of exception handlers. The same line of code was the reason behind multiple vulnerabilities before, but they are targeted another part of the check. And the most interesting is how this vulnerability was fixed. Even if the source code is that we can find on GitHub is more than 2 years old, the fix of this vulnerability is still here. It was fixed like this. So the basically the root case of this vulnerability is that they forgot to check whether this function may be called twice, so it wasn't intended. So it's a logical vulnerability. Since exploitation of this vulnerability allows to execute unverified bytecode, exploitation becomes simple. When the interpreter comes to interpret a throw instruction, it simply changes ABC-based program counter to the position of exception handler. And in this exception handler with malicious instructions, we can see that whole method of x1d is called, and x1d is an index of function c0 f2. And whatever is passed here as persistent is passed as an instance of this class. And in this exploit, we can see that as an instance of C0 class is passed another instance that extends system class graphic control parameters. And in this case, 0.5 will point to byte array object, and substitution one will convert this object and will retrieve its pointer that will be used later to corrupt the byte array and get arbitrary read and write. But at this moment, arbitrary read and writes are already achieved with ability to write this to 0. This address points to root of table of graphic control parameters, and with ability to write it, it's possible to use these functions as gadgets to read and write arbitrary memory. So, why to target in repetition mode? Since try from and try to ranges are not set, this code exception handler will be not compiled in just-in-time compilation, even if the vulnerability that was exploited in Verifier is common for just-in-time compiled in the interpret mode. So, how is it possible for us to quickly analyze this exploit? The binding of interpret code is easy, since execution of all interpret code is performed inside one function called interboxer. It's enough for us to just write a Python IDPO script to name our entries in jump tables to their appropriate code names, and then we can just follow the execution. But what about debugging of just-in-time compiled code? Well, debugging of just-in-time compiled code is quite tricky experience, and it was addressed multiple times before. The first concept was presented by HealthAV, and unfortunately it wasn't ever released, but the ideas from it were used by all other solutions. And this idea was to set hooks, special functions that may resolve methods and then just use it information. A few years later was released SOOP2. It's not a debug library, but rather an instrumentation tool. Unfortunately, it works only with old Flash versions, and it seems too hard to port it to new ones. Debug Flash tool probably is the first DBG plugin that was released to public. It works great because it supports signatures, so it may work with different versions of Flash. And then was released a Python script named DBG, and it works great with emphasis on hit locations and exploit writing. But we analyzed error source code and found out how was it possible for us to further increase experience while debugging just-in-time compiled code. So while I was debugging just-in-time compiled code, I paid attention to some sequence of instructions that were setting some incremental value to the incremental value. So I raised the question, what it is? And the answer was found in the code responsible for generation of just-in-time compiled code. In just-in-time compiled code, CVIP is local storage of current ADC-based program counter, and it's used for exception handling. So it's present only when this method has exception handlers. And making casual exceptions to return true for each compiled function method, we can see that in this case, this CVIP will be forced for each compiled method. So our plan was not only to create the portable Flash plugin for debugging of just-in-time compiled code that will work with different versions of Flash and will be very easy to support, but also significantly improve this experience of debugging just-in-time compiled code. Since we already have an ActionScript3 processor model, it's possible for us to store information about each deassembly construction and then transparently resolve it during debugging of just-in-time compiled code. Here you can see the example of just-in-time compiled code without plugin. And here's a quick demo. So basically, I'm attached debugger to the Internet Explorer with Flash. But prior to that, I set up a breakpoint in our plugin to this exact function. And when I hit run, this debugger continued to execution and hit these functions that apply. And here you can see that our just-in-time generated code was enriched to show all the bytecode instructions in the right place where they will be compiled. So basically, with this plugin, we have opportunity to debug just-in-time compiled code, like in the way if we were debugging bytecode. We are exactly on the same level, but we have, since we're debugging in the highest level, we have like good more opportunity to debug this code. We can change memory, we can change any registers, we can change the control flow. Basically, we can do everything. So the conclusions are that event core was and still the source of critical vulnerabilities, and more execution modes leads to more exploitable bugs. This source code of our plugins are released under GPL3 and available on our GitHub and also on hextrace.com plugin contests page. And here is the bonus part. The vulnerability that we were talking before was found in 2017, and this year was found another vulnerability that is as well related to bypass authentication handler. And here you can see the function that triggers this vulnerability. And in this case, exception handler will be recalled if any exception in defined range will cause an exception. But in this case, in this range, there is only jump instruction, and this instruction never causes any exceptions. So how does it work? In this case, read8 instruction, which is float 8-bit integer, will cause an exception because provided value is too big to fit into 8-bit integer variable. So if we will take a look at V800, we will see that we will call a more brain-check function. And if we will check it, we will see that this function simply throws an exception, and interpreter will try to find the exception handling that is shaped to this address of this instruction that causes an exception. And if it will found it, it will execute this exception handler. And yes, which exception handler will be called in this case? Well, since XPC variable wasn't set, it's not initialized. So it equals to 0. And the 0 is the index of jump instruction. So the root case of this vulnerability is basically that they forgot to use macros save XPC. So yeah. Thank you everyone. Do you have any questions?